So, welcome back once again. The next session is uh, neural networks, the engine of modern AI, and the session is handled by Professor Pillai Praveen Thulasidharan. He is with the Department of Computer Science and Engineering, the Rajiv Gandhi Institute of Technology, Kottayam, and he has got immense amount of experience in both industry and academia. He has worked in industry for quite a few years and later moved to NSS College of Engineering, Palakkad, Kerala, and then to Government Engineering College, Idukki, and now with Computer Science and Engineering Department, Rajiv Gandhi Institute of Technology, Kottayam. Uh, he is a research scholar of Indian Institute of Information Technology, Kottayam, and with all your permission, let me welcome Praveen sir for this session. Thank you.
Thank you, sir. Am I audible?
Yes, sir.
Yeah, just give me.
Yes, sir.
Hope the slides are visible.
Yes, sir.
Yeah. Okay. So good evening, all. So we can start with today's session. So my session deals with new. So,
sir, I think there is some lag in the. I mean, maybe you can turn off your video when the presentation is running.
sir.
There was a kind of jitter. So I think it is better to turn off your video. You are presenting the screen, right?
Yeah. Is there any problem, sir?
Now it's okay. Anyway.
Yeah. Okay, sir. So just we can have the overview. So what so in this session we are focusing on the basic aspects as such. So we'll be seeing what new we can learn. So first one, so the first discussion what we can have is we can compare the neural networks with the conventional methods. So what all methods we have learned right now, we have discussed till it. So we can just try a comparison on it. So how this neural network or the neuron sort of thing differs from the conventional methods. The main point of discussion would be why we brought in neural networks when we already have a set of other conventional methods. The next we can discuss on the neural aspects. So apart from the structural and other aspect, we can focus on the explainability aspect of the neuron. So what behavior a neuron plays when it is integrated with the network, or simply in a standalone fashion, how this neuron would behave. And we can also focus on the constraints while interconnecting. So network is something like the interconnecting neurons. So there are some constraints. We cannot connect each neurons in any way. There's some constraints. So we can discuss on that also. Finally, we can look into the feed-forward neural network, which is the basic, the first sort of neural network which came into things. We can focus more on its interpretation aspects rather than the architecture and learning. I think most of you might be dealt with. Then if time permits, we can go with the implementation aspects. We can see a sample code as such and common frameworks used. Okay, so you can just interpret me in between if there are any questions or sort of thing, we can discuss and we can move forward. Okay. So starting with the foundational aspects, we can say that any machine learning, right? So what all machine learning model we have learned, we can mathematically represent it as a optimization. Now, what the optimization problem focuses, we are trying to estimate an optimal model. Now, this model is defined with a set of parameters. Now, in machine learning paradigm, we call this model as a hypothesis. We call it as hypothesis denoted normally by h of theta. By theta is because this hypothesis or model is actually defined or mathematically equated with a set of unknown entities, which actually we need to estimate. And how that estimation or the process of estimation is guided, it is actually guided through a objective function, or in terms of machine learning perspective, we call it as the cost function. Now, in a supervised learning, this cost function is a function of the output generated by the model, estimated model, and the decide what output we actually require. So it compares both, and it gives a value. If the value is larger, we say that the estimation is not good. It's sort of a bad. And if it is less, we say that the estimation is something like the estimation is progressing in a correct manner. But need not always this cost function be means it's a penalty sort of thing. In sometimes it comes we can formulate the machine learning in this manner also. That means we are shifting the minimizing problem to a maximizing problem. So it all depends on what nature of problem we have, how we formulate the model, and how we guide the estimation of the parameters. So sometimes there are cases like wherein the objective function or the which is the guiding process, a combination of both the minimization problem and the maximization problem. So for instance, it will be the again the adversarial learning where the loss function what we have designed is it's a combination of both the minimization as well as maximization. So in general, we can say that any machine learning problem is something like an optimization where we are estimating an optimal parameter for a defined model. Now, I think in the last few sessions, we have gone through many conventional models, and just repeating, we can just find out. So our intention here is just to understand what actually this model and means each of this. Hello. Okay. So what these models are and what actually the implications we have done. So first we take the simple linear regression. I think in a simple linear regression model, we have only one input. That means we call it as the X. Now this X represents the feature of the sample. Right? So in other words, I can say that I have a data set where there are data points and each point is represented by a single feature and a single output. So output means from this single feature, I want to get the corresponding output. If you take simple linear regression, the hypothesis, the model, what we are learning is simple line. So there will be n number of lines in that space, and we have to come up with an appropriate line. Right? And what is guiding our estimation is the mean squared error. I think you might already have defined, seen it. Now to geometrically represent it, we have the input space here where the x-axis is shown as the input and the output. Now, what we are trying to find out is trying to find out and approximate the optimal line. So which line will be the optimal? The line which passes through maximum number of points. Right. So there may be n number of lines. So we are interested in only that line which passes through maximum number of lines. That's what the simple linear regression does. Now, the other aspect what we have to focus here is a simple linear regression model is able to learn only a line. I mean, it is a one-dimensional thing. The model is restricted to a line. It cannot learn any other representation even in a one-dimensional space. It cannot learn a circle. The restriction is we are imposing the restriction that the model should be a line itself. If you take a multiple linear regression model, again, the boundary surface or the thing we are learning will be a hyperplane, right? So it's the same thing. The hypothesis plane will be depending on the number of inputs. It can be a plane in a three-dimensional space or other. So a higher dimension we call it as a hyperplane. And the thing which will be guiding our estimation is the mean squared error. Again, I have shown a geometrical representation wherein we have two features, x1 and x2, and we have the output. Now our hypothesis space is coming up an optimal plane on which most of the points will be lying. So those different points should be lying on the plane. So that is what the intention is. The restriction here is we are restricting our hypothesis plane, hypothesis space to a plane. Now, if you take a non-linear regression of a polynomial regression, the hypothesis space is non-linear curve. Right? We can also call it as a manifold. So the higher the non-linear curve in a higher dimensional space, we normally call it as a manifold. Now this is where we fix it here. That actually I am estimating now the hypothesis. What I'm estimating is with a degree of 2, and it will be something like this, which I have estimated. But need not always can be this big. It can be different. Right? It can be just shifted. But for a second degree polynomial, might be always be having, it will be a sort of a convex something, one bend it will be having. Okay. Now again, SVM, just you saw in the last session, we are finding out a line which will be, or we are actually estimating the margin, the maximum margin which separates the two classes, and we usually find a plane. Okay. Now for this, the hypothesis space will be a margin maximizing hyperplane, which separates it, right? And we use this as the representation. And what is guiding our estimation is the hinge loss. Okay. Again, moving forward, this is something the decision tree. So geometrically, if you're seeing the decision tree, the hypothesis space is something like axis aligned recursive partition. What this mean is, suppose we are finding out a rule. Now it will partition each of the feature axis. Now feature X, it can be it will be a horizontal partition, I mean vertical partition, and for X2 it will be a horizontal partition. So actually we are trying to find out something axis aligned partition in there, and based on that we are getting it. And for a Navy base, actually we are fixing this. We are actually finding the likelihood and the prior probability. And what we do is we actually fix it that the likelihood might be a Gaussian distribution or something. Mostly we fix it to a Gaussian distribution sort of thing. Now, all these conventional methods have one thing in common. Actually, we are under the idea that we know, the intuition is that we understand the data set, the relation we know. It might be a linear relationship, or we know the density or the probability, and we try to enforce a particular model on that data set, which means the hypothesis or the model we are estimating remains fixed. There is no chance that we can change it. That is one of the major problem with this conventional model. But in reality, the relationships between the data samples are much more complex. It might not be linear always. And that is why we get outliers in linear regression or some false classification, the classification model. So mostly this relation is complex, and it might not be able to predict with this sort of fixed hypothesis. And there the role of neural network comes in. Now, basically, the neural network has three major importance or ability or potential within it. One is it does not restrict it hypothesis space. So we call it as the decision boundary. So we not so predefinedly or in earlier itself we don't fix it that we need to learn this particular hypothesis or this particular model. Now the decision boundary is unrestricted and it can be learned as the training progresses. Now, for instance, I've shown two plots here. The first is for the logistic regression. Now, you remember logistic regression always learns a hyperplane and it converts it to a probability value. Now, your red colored samples are for one class, the other is the second class. The class 2, the positive and the negative class. Now, the separating boundary is linear. We already discussed it. Why? Because the hypothesis is a linear, and so the boundary space is also linear. But for a neural network, we are able to learn something like this as a nonlinear curve itself. With the same configuration, same number of neurons, same number of architecture, as the data set changes, this nonlinear curve or this hypothesis space can change. So that means we are not restricting the decision boundary. It's something like open during training, which we can learn as such. And the second ability is feature learning. And this is one of the most important aspects. Today's generative learning aspect is all based on this feature learning aspect. So in linear regression or the other conventional model, it is the programmer or the data analyst who have to design the feature as such. So depending on the data set, its properties or sort of thing, we have to come up with a set of suitable features and we have to feed it into the model. But for neural network, one of the aspect is even we feed them with the model features, it has the ability to learn from that feature. So it can extract new features. That is what one of the feature which makes this neural network separate from the convention. And the other act, it can act as a universal approximation problem. So this is basically related to the feed-forward network. So it is theoretically said that any function or any non-linear, linear, any sort of function can be learned by a feed-forward network. But it all depends on the data set, what we have, and how the training progresses as such. Okay. So one of the aspects from here, what we can take forward is neural networks, compared to the conventional network, has some more ability. So one thing is it releases the restriction on the model or the hypothesis space, and we can learn any number of any sort of, not any number, any type of decision boundaries. Okay, now let's start with the neural network. Now, structurally, we say that a neural network can be thought of as a connection of neurons. So the basic unit composed, which is used for building a neural network is the neuron. Right? So it is of interconnection of. I think neuron, most of you might be aware of, or you might have come across sometime. So basically, mathematically, a neuron, we can say that it is actually two consecutive operations. So even though I have shown it in a diagram, mathematically, I can say that it is a collection of two operations and done in a consecutive manner. The first operation, or the unit which does it, we call it as the summation unit. And second thing is an activation function. Now, this is the activation function, or we also known as the output function, which is applied on the output of the summation operation. Right? So this summation operation, so if I take a neuron, this summation operation remains fixed. So we cannot change this summation operation. It is it remains for all the neuron. But what is flexibility given here is we can change the activation function. We can decide what function to be applied on the output of the summation operation. Okay. Now, the summation operation takes input. This is where the input, the summation unit is the one which is accepting input. If I have a sample which is described by n features, so those n features will be given as output. So the x1 will be first feature, x2 will be the second feature. In that way, I have n features. That means if I have a sample with 10 features, it will be x1 to x10. Now, apart from this input, there is one input which is remain fixed, the x0 input. Now, this x0 input is something that it always remains 1. That is fixed. That is not changed. At a given moment, we feed only one sample. That means the attributes, the features related to only one sample, we give it to the summation. Now, each input is associated with a weight. It's a numerical value. Can be a floating, positive, negative, any value. So each input is associated with a weight. For instance, x0 is associated with w0, x1 is associated with w1, and xn is associated with w. Now here, the w0 weight, we call it as the bias. W0, a special name we use, we call it as a bias. The others, normal. What happens here is the x1, the inputs are given by the user, and these are the parameters of the. So parameters means these are unknown. Based on our output, we have to estimate it. We have to learn it. That is what we call it as. Okay, so including the bias, the W1, W2, all the weights we have to learn. Right? So at the start of the operation, we can initialize it to any random values. But if you want to get the desired output, we have to estimate what value it should contain. And that is what the process, we call it as the learning process. Okay. Now once it comes to the summation unit, the summation unit does the weighted summation of each input. So weighted summation is x0 into w0 plus x1 into w1 plus x2 into w2, xn into w. That's what is being done by the summation unit. Just does a weighted summation on, and it adds all the weighted. right? So x0 into w0 plus x1 into w1 plus n. So it just multiplies it and adds it. And what the resultant value gets, we call it as the activation value. Okay, so the summation unit generates a value, we call it as the activation value. Now this activation value acts as an input to the activation function or the output function, and we get the output. Okay, so the output function, when applied on the activation value, we get the output as such. Okay. Now mathematically we can say that in a matrix operation, we can say that S can be obtained by W transpose X, where W is W0, W1, Wn, where W0 we call it as the bias, right? And the input X equal to X0, X1 till Xn, where X0 is will be always be 1. So a single neuron will be in this fashion. What is our objective? We have the desired output. If it is a supervised learning, we know the desired output for a given input. We try to come up with the estimate appropriate values for W0, W1, the other weights, such that we get the desired output. So that is what we call it as the learning process. So this is what actually we need to come up. So for that, what we do is we come up with the loss function, L, or we call it as the objective function or the cost function. So what it is, so it's a function of the B. B here denotes the desired output, and this is what the output of S. So we can say it as the S. Now what we need to do is we have to minimize L. So we have to find a set of W such that the L will be the minimist value. That is what mathematically we call it as. Okay. And for that, we use the learning algorithm. We call it as gradient descent. I think you might already have learned in the linear regression sort of thing. So what gradient descent says, you go, it is an iterative algorithm wherein I can update the weight value. Okay. How the weight value is updated? The next weight. So if I apply an input, I know the error. So which manner the weight has to be adjusted is given by Wi minus delta Wi. This is the current value, and I plus 1 will be the new value. And delta Wi is calculated by eta into dl by dou L by dou W. That means eta is the learning parameter. Normally it will be ranging in the value closed interval of 0 and 1. Normally it will be 0.01, 0.25 sort of thing. And this is something like derivative of L with respect to W. That means which weight you want to update, right? With respect to that, you take the derivative of the loss function. You get a value and you update it minus that value. So you keep on doing this, keep on doing this, doing that until you get the minimist loss. So what value you get for W0, W1 for that? In that manner, that will be the optimal value for that particular. Okay. So this is what normally happens for a single neuron. So in a matrix formation, we usually denote as nebula operation, where nebula is depending on the number of weights, we are differentiating with respect to that particular weight sort of thing. Okay. So this is what a simple neuron happens. Now just we can dive more into the neuron as well, because this is the normal operation as such. And if we get more into those specific aspects, this is the summation unit. Okay. Now what the summation unit does, as already told, it just takes the weighted summation. So this is the weighted summation, right? Since x0 is 1, I haven't written x0. So w0 plus w1 x1 till wn x. If there are n inputs, this will be the normal form of the activation value. This is what the activation value does. Okay. If you observe this, you have come across this equation. This is something like a hyperplane sort of thing. Now, when we give an input to this equation, we get three sort of values. Normally, it will be the interval of minus infinity to plus infinity. Now, for our understanding's sake, we say that we either get 0, or we get a positive value or a negative value. Right? So for some set of inputs, we get 0. For some other sum, we get a positive value. For other sum, we get a negative value. Okay. Now let us understand with the set of plots here. So I have taken the first plot. I have taken only one input. That means only x1 is there. Nothing else is there. Okay. What I have taken is I have taken that w is 2. That is w1 equal to 2 and w0 equal to minus 2. Okay, so I have taken this. So I have already decided. So that is what we have estimated. So somehow I have estimated. If I am doing this, what I receive here is I receive a point here, x equal to 1. Now, if I substitute x equal to 1 in this equation, I get a value 0. Right? I get a value 0. Now, any value greater than 1 will result into a positive value. Right? So, if I substitute here 2 into 2, 4, minus 2, I get a 2 value. So, it will be positive. So, any value greater than 1 will be resulting into a positive value. And any value less than 1 will result into a negative value. So actually I am getting something like a space here, region here, right? So I get a region here, positive region, negative region, 0. Right? The same, I have again taken a single input here, but I have just changed the W value. So I have taken my W1 as minus 1.5 and W0 as minus 2. Now it shifted, right? Now what happened here is the positive and negative value just shifted. Now the negative value shifted to the right of the point, but the point also has changed. It is minus 1.33. But earlier it was on the left hand side of the axis. Now it is on the right hand side of the axis. The input is the same, right? So we can infer here is based on this, we get a positive and negative region. If there is only one input, it can be either to the left or to the right. That is what we have. The positive set of value, 0, negative. And if I take two inputs like x1 and x2, again I get a plane. I have just used a two-dimensional representation, so that's why it is seen as a line. But actually it will be a plane sort of thing, wherein the positive and negative will be either on the upper side or the lower side. Right? So if there is a one input, if it is left or right, or if it is a plane, it is on the upper side or the lower side. So here saying the two inputs, now here it was on the lower side, the positive region, but here it is on the negative region. Right? It has changed. If I take more than two inputs, like three inputs, now I get a three-dimensional plot. It will be a hyperplane sort of thing, wherein it will be something like lower, below, front, back sort of thing. Right? So the summation unit, what we have to understand here is, within a summation unit, when the values are given, we get two regions sort of thing, where one is concentrated by a positive set of values, the other by a negative set of values. Okay, so that is what the summation unit does. Now, on this positive negative value, we brought in the activation function. Okay. So activation function where something like we apply this f on this value. So this will be positive, negative, or 0. So that is what we the summation unit value what it generates. Now, this activation function can be different types. So some of them are linear. It's a linear function. So f can be a linear function. What is a linear function? It does nothing. F of x equal to x. That means whatever it accepts, it will give as it is to the output. Okay. So if it is, so here the x is showing the input to the activation function or the output function. If it gets 1, it will output again, minus 10, it will output minus 10. So whatever it comes as input, it gets output as such. Okay. The next is step function. Now, what is the step function? Now, this function maps the activation value to two discrete values. So it maps only to 0 and 1. Right? Now, what will be 0? Any value which is less than or equal to 0 will be mapped to 0. See here. So any value which is 0 or less than 0. So this value, right? Any value which is 0 or less than 0 will be mapped to 0, and any value which is greater than 0 will be mapped to 1. So there is a mapping happening, remapping happening. So earlier we had only positive, negative, and 0 value. Now it has been remapped to binary values like 1 and 0. Now if you take ReLU, here the remapping happens only for values which is less than or equal to 0. Other values are given as such. Right? Here we have 0. And negative values are mapped to 0, while others are passed as on. That means the positive values will be coming out. Whatever positive values, so it will be something like the range will be 0, infinity. So it will be something like 0, close 0, and infinity value. Same thing. Now the other activation function can be sigmoid. What is the sigmoid? It does sigmoid. It remaps the output value to the range of 0 and 1. So any value you give, the output value for this activation function is 0 and 1. But let's see which value will be mapped to which. So here if you see 0 and less than 0 will be mapped to a range equal to or less than 0.5. right? So if I say that a sigmoid function is outputting a value like 0.5 or less, it will be actually, the activation value will be 0 or less than 0. If the activation value is more than is positive value, it will be mapping it to a positive value. Means it will be mapping to a range between 0.5 to 1. That is what the sigmoid function is. If I have a tanh function, output function, the range is 1 and minus 1, where 0 will be mapped to the activation value of 0, and the positive value will be mapped to 0 to 1, and the negative value will be mapped to 0 to minus 1. So this is what the activation function does of tanh. And if it is leaky ReLU, it is similar to ReLU itself, rectified linear unit. The only difference is it relaxes constraint on some negative, some range of negative. That means some range of negative values will be passed as it is. Right, positive value anyway it will be passed as it is, but some negative value will be also be passed, and others will be missed. Okay. Now, what the idea, what we can summarize here is the activation value using the activation function or the output function gets remapped to a new range of values. Right. So that is what the basic idea here is. So I have a positive, negative, 0 value, and I'm bringing the activation function of the output function, which remaps it to another range of values, and that provides meaning to a single neuron as such. Okay. Right. Now let us understand what actually, if I take a neuron, what actually it behaves, what will be the behavior of it, or how I can interpret it. Now, basically, if I have a neuron, there are only two things which it can do. It can either act as a boundary partition. Boundary partition is, I have an input space. It is basically used for classification. I have input space. I have to classify it into different categories. So that is what is meant by boundary partition. The other is feature transformation. Now, the first question which comes into our mind is, we have seen that the neuron will generate values. The output function will be remapping it. So any neuron will be generating those range of values. So if I'm using a sigmoid function as output, it will give 0 to 1. If I'm using any other ReLU, it will be giving. So how come the same value will be acting as a boundary partition? And how come the same can be used as a feature transform? That is what we need to understand. So feature transformation is something like we transform the input data to some sort of other values. Now here, we have explained the boundary partition sort of. So again, boundary partition is used for classification. Now, classification is something like categorizing. So we have to understand the range of values. Now let us understand. So let us see that suppose I am using a linear value. So here the plot is something I have used a dummy data points when I have generated values. So the red values shows the positive value. Positive means those inputs which have generated positive value from the summation after the linear. So linear unit means it's something like the input is given as such as. Right. Now the Z here, what we have shown here is the activation value. Okay. So here the red thing is something like the positive value. Right? The positive value sort of thing, and the 0 is 0 value, and this is the negative value. So here I can inherently we are getting two classes. The one represented by the positive values, the other represented by 0 and negative value. Right? So if I have a neuron and if I want to perceive, or if I want to see it as a partition thing, one way of doing it is you estimate the value in such a manner that the data points belonging to the positive class or the class 1 generates only positive values, right? Through linear output. So the weight should be adjusted in such a manner that it generates positive value, which can be called as class 1. The other, we have the negative value, which can be created as the. Okay, so I can observe the same thing. So I can view or perceive a neuron through linear output in this manner as a classifier. Okay. If I have a step function, inbuiltly step function does outputs only two values, that is 0 and 1. So there itself we can say that the value which is generated denoted by 1 will be class 1, the other will be class 2. So I can have partition there itself. ReLU again, so ReLU has something like a positive value and 0. So the range will be positive and 0 sort of thing. So here also I can say that those generated by positive value can be treated as class 1, the other as class or the other class. Okay, so in this manner, we can say for each sigma. So here also we can see the sigmoid function. So you remember I have said like 0.5 is the value which generates 0, right? So any value that, so the positive value will be mapped to 0.4, means 0.5 and less, right? So this can be treated as class 1, first one class or the other class, and this can be treated as class 2. Okay, so the red will be class 1, class 2. So it only shows the range of values and how we need to perceive things. So if I have a sigmoid function and if I want to view the neuron as a classifier, as a partition, so what I have to do, I have to view that a set of class, a category of class should be mapped to a particular set of values. The other should be the other. Okay, so this is something like the tan h, wherein I have 0 and less than 0 will be one class, the other will be class. Okay, and this is decay. So inherently, I can say that if I have a neuron, I can use it as a partition, but only it can be used for binary partition. So it can be used only for binary classification problem. We cannot come up with a multi-class classifier for a single neuron, right? Since I have only one output, and these are the range of values which we have. So it can act as a classification for binary classification problem. We cannot bring in multi-class classification problem. Okay. Now, feature transformation or feature transformer, when the neuron is acting, it is something like a peculiar thing which is actually currently the modern neural network architecture is exploiting it. Now, it is something like instead of taking that value as it is, we are actually taking it as the features or the characteristics embedded within that data space. Okay. To explain that, what I have taken is I have taken a sinusoidal ring. This is just a pattern where each point represents a data point. So it is in a 2-dimension. I have a x1 and x2. So I think it's a 2-dimensional having 2 features. So it's just a coordinate space. Okay. What I did is, so I designed a neural network, a single neuron, which takes 2 input and one will be the bias and 1 output, right? So we have something like positive and negative values. If I'm using a linear output, that means the linear function as activation function. So I will be getting something like this, right? So all the red color will be positive, greater than 0, right? And all the negative will be, blue color will be the negative values. Okay, so even if I'm not using the linear function, the summation unit will generate this as the output. Right? So we get the values which is greater than 0, less than 0 as 2 different entities. Okay. Now for feature transformation, we don't use all the activation function. Right? We restrict our transformation or activation function to a set of. We normally use ReLU, leaky ReLU, and tan h. Okay. Now again, what happens is we are applying this ReLU function. What we get is we get a sum part as 0. So this part is 0, right? And this is something positive value. Now it has been remapped to a new data space. Right? Now, if you can say that during partition also, we saw the same data output value sort of thing, right? But actually we are perceiving it in a different manner. Same thing, but perceiving in 2 different forms. When a neuron has to be acting as a partitioner or a classifier, we try to attach it to sort of a class sort of thing, where one category of values will be associated with one category of class, the other will be with the other. And when I am using a feature transformation, I say that the new generated values or the new data, it corresponds to a new data space or a input space value sort of thing, right? And we believe that that data space contains some inherent properties of the input features. Okay, now what features will be working on? We will be working on this sort of data space further, right? But from a single neuron, I will be transforming the input space into another data space. Here, what it will be, if I'm using ReLU, it will be mapped to a value between 0 to infinity, and that my data space changed. Okay. If I use a leaky ReLU, similar to ReLU itself, but only thing is some portion of the negative region will also be into the data space. I'd say it depends on problem to problem. Sometimes in a neural network, some problems we will be discussing in coming slides. Then when using ReLU, means leaky, if we use leaky ReLU in place of ReLU, we get more sort of performance sort of aspects. Okay, and tan H, now the activation space changed, right? The data space changed to 1 to -1. Now the same thing, it is actually the same thing if I say the data partition or classification, the same set of values, but I am perceiving two different things from them. One I am using for identifying the classes, the other actually I am transforming, I am looking those values as a new data space where I believe that some characteristics of the input features are embedded, or I can work on it for further. Okay. Now these are the two aspects which a neuron actually works in a neural network. It can either act as a partitioner or it can act as a feature space. If you take what role this plays in modern architecture, if you take the multiple, which is the feed-forward network, the neuron in the output layer, which we'll be discussing, will be acting as a partitioner, as a boundary partitioner. In CNN, that is convolutional neural network, again the classification at the last portion, when you it will be in the neurons in the last layer will be acting as a partitioner. Similarly, in transformers, MIL, these are the areas where a neuron, if you take a neuron from that layer, it will be moreover acting as a partition. That means it will be looking at the values which it is generating for a boundary separation aspects rather than a data space where the characteristics are embedded. Now, where the neuron outputs are taken as a feature transformer sort of. So we have an autoencoder, which is a self-learning model sort of thing. Therein we have a bottleneck features, right? So when in those areas, the output of the features, the output of the neuron is considered as a new feature space sort of thing, right? In CNNs, see, in CNN, we have the CNN here also and here also. In the same architecture, same network, the neurons in different parts behaves differently, right? In the classification head, the neuron acts as a partitioner, but in the convolution layer, it acts like a feature transformer for extracting features. Similarly, in transformer attention, MIL is multiple instance learning encoder. So these are high level sort of architectures wherein the neuron plays different. So if you take a particular neural network, the role that a neuron plays is basically either of a partitioner or a boundary partitioner or of a feature transformer. Now within the same network, the neurons, different neurons can play different roles as such. Okay, so this is what we call it as if someone asks you the explainability or interpretability aspect of the neuron, we can surely explain what actually happens with a single neuron as such. Now comes about interconnecting. Interconnecting is something like we have a network. So normally network will be an interconnection of neurons. So ideally, the first question is how to connect two neurons sort of thing. Now, connecting neuron means I am taking the output of one neuron and giving it as an input to the other neuron. But when connecting, we call this as a connection. This is one input connection. This is the output connection, which is giving us an input connection to the other neuron. Now, each connection is governed by a weight. So if I give an input, it should have an input as well as a weight. That means a parameter. So if I take the output and connect it to B, the output coming here will act as an input and there will be a weight. Okay. Now, in what different ways we can connect? Normally we have three ways, right? One way is I take the output of one neuron and give it as an input to the other neuron. We call it as a feed-forward connection. That means there is nothing, just feed-forward sort of thing will be happening, right? The other is we take the output, right, and connect it as again as the input to the same neuron. This can be done. Again, this will be governed by a weight. Okay, so this connection will be there. There will be a weight here. There will be a weight here. That means a parameter there. So I can take the output here and again connect, and this is what we call it as the feedback connection. Right? And I can have these connections also, right? So I can take the A's output and give it to the input to another neuron, and take the same output and take as other neuron. Right? So these are the most commonly used. But so one is called as the feed-forward, feedback, both. Right? So theoretically, if we say we can connect any two neurons or a set of neurons in any manner. Right? I have so if I have a wire and connection, I can connect it in any manner. So there is no theoretical restriction as such on which manner we should connect it. But all the connections or the manner in which we connect neuron, all connections or all topology might not be good enough. And why? There are two constraints on it. So we need to connect the neurons constraining two aspects. One is the computational constraints. Okay. Constraints. And now the computational constraints is actually we know that we have connecting neurons. Each connection is bounded by a weight. And our ultimate objective is to find appropriate weights for all these connections, right? Or we have to learn those weights or estimate those weights such that we get the desired output. For computing these weights, we generally use a learning algorithm, a gradient descent, or a sort of other version of another version of other add-on additive on to the gradient descent algorithm. Now, for the gradient descent or the gradient sort of thing, or to work, one aspect is we require the connection should result into a directed acyclic graph. Right? Should be directed and it should be a acyclic. That means what happens is if I take a neuron, the neuron as a single node, right, and the connection to it as edges, right, and if I try to visualize it as a graph, it should actually result into a directed acyclic graph. The reason why this is we will be seeing that during learning of weights, we depend on the gradient of the output function and also the input. Now, this gradient and the weight should be tractable. That is what one of the problem during learning is. Now, if we come across a topology where these values cannot be tracted or we cannot be reversed back, it will cause a computation or it will not work. So that is one of the problem. And even though we have cycles like in recurrent neural network or feedback connect, we have to do something like we unroll it or unfolding of this so that we can get the directed cyclic. Okay. And the other aspect is, see, everything, these weights, this activation function, all these are computational things. We need the summation unit, the multiplication, applying of activation function. If we design or we come up with a topology with enormous number of neurons, connections, weights, all these weights should ultimately be residing in a computational memory where a program is running on it. Now, those memories should be feasible. If it is going out, it's very dense and the connections or the weights, which is not occupied by the memory, it will lead to a crash. So first constraint which determines the topology is the computational constraint. So the major out of this, even though memory we can add on sort of thing, one aspect which is very much important during computational aspect is the weights of the gradient should be tractable. Right? So that is one thing. Okay, so the one constraint. The other is learning dynamics. And so learning dynamics is the updation, the weight sort of thing we have seen in the single neuron where the weight is getting updated. Now there's some problem comes. We call it as the vanishing and the exploding gradient when the topology or something like it increases. Right? So we come across some other problems. We call it as vanishing gradient and exploding gradient problem sort of thing. So one thing is we cannot connect neurons in any manner. So when we are creating a topology, we should keep these sort of things in mind, wherein the computational constraints and learning dynamics should come into effect. This is what will be governing our model. So using this, the famous topologies, right? So based on this constraints or following these constraints, there are a number of topologies which we have come across. The first one, the simplest one is the feed-forward network. I think almost all of you might have heard of those things, this network, wherein the network connection is fully connected. We can see what is meant by fully connected, right? And the data flow, right? So the operations, you remember the summation, activation value applying, then it is given to another neuron sort of thing. So that flow of data is only in one direction. That means there is no feedback layer as such. Okay? So only one-way flow is there. So that is what the connection characteristic is there. It is predominantly used for classification application, this particular architecture as such. Okay? And we have this something like we call it as the universal approximator. And why it is called, we can just see it. Okay. Right. Then we have the convolutional neural network. Now, convolutional neural network, you might be dealing in the next tomorrow's session. One of the important aspect there is we have local receptive fields, right? This is something like we call the convolution layer, wherein we use it for feature extraction. Right? It is predominantly used for image recognition and medical imaging. And now we have the recurrent neural network, where we use the feedback loops. Right? So all here in convolution neural network and feed forward network, the connection is something like the data flows in on the only one direction, the forward direction sort of thing. But in recurrent neural network, we use a loop sort of connection. We call them as temporal connections. Right? And it is commonly used for time series analysis and speech recognition. I think you might have come across transformer architecture, one of the hot topic or topic jargon over here. So it uses an encoder decoder architecture, attention mechanism sort of thing. Right? And other, we have a graph neural network. Right? So it is something like where we are using graph representation. That is one of the most important, one of the emerging area, wherein we are using graph data in machine learning. We know that graph data is normally something nodes, it can take different shapes sort of thing. But graph neural network helps to learn or achieve learning through graphs. Sort of thing. Now, one aspect is each of this model has a predefined architecture. And these architecture follow the constraints or obey, has overcome those constraints. One is the computational constraint and that is the learning dynamics. So they have especially defined, means they have stated how to adjust the weights, what happens when the is passed from, means the gradients are passed. All those aspects have been clearly dealt in this sort of thing. Okay. So these topologies actually have come across obeying the constraints of the which we have discussed. Okay. Let us discuss the feed-forward network. The feed-forward network, what we have here is, sorry. Now, again, a feed-forward neural network is a type of artificial neural network where the information flows in one direction. We have already told it. Okay. Now, what happens here is, normally a feed-forward network is an interconnection of neurons. What we have done is we have organized the neurons into layers. Now, what is a layer? Now, a layer contains n number of neurons, means any number of neurons. The peculiarity there is none of them are interconnected to itself. That means a neuron belonging to the same layer will not be connected to among themselves. Okay? So that is what quantifies a layer, what we call it as. Okay. Now, what are the different types of layers in an feed-forward network? I have basically three types of layer. We have input layer. Okay. So input layer, what it does, it just receives the data, right, and it just passes on. So normally it can be pixel values, features, and sort of thing. That is what we normally has as the input. Okay. The other layer is hidden layer, and the other is output layer. Right? Now the hidden layer actually it works for the data transformation or using weights. It just transforms the input value to another set of values, and output layer is something like generates the final prediction value. Okay. Now let us see this as a from sort of a okay. So this is a typical example. Right? So normally we call this first layer as the input layer, okay, and the last layer as the output layer, okay, and in median we call it as the hidden layer. Right? Now, as stated earlier, if I say a layer means it's a collection of neurons. So here, if I say the input layer here, so here the input layer contains P neurons sort of thing. Right? Now, what the peculiarity of a neuron is, it is not connected to its the other neurons within that layer. Right? So it is only connected to the neurons in the preceding layer. So there is no connection here, no connection here, no connection here. Okay. There is one more restriction here. The neurons belonging to the same layer, right? So if I say this is the, this green color is the neurons belonging to this input layer. This blue color is belonging to the first hidden layer. This is the second hidden layer. This is the third hidden layer, right? Now all these neurons will have the same activation function. That means the neurons belonging to the same layer will have the same activation function. Suppose the activation function of this neuron is ReLU. The second neuron should also have the activation function as ReLU. The third should also have the activation function as ReLU. Right? And here, suppose it is TANH. The other should be TANH. Right? So if I say a layer means, the definition is it is a set of neurons where there is no interconnection among themselves. Right? It has the same activation function. All the neurons will have the same activation function. Okay? Now, let us see. So this is the input layer, right? So we understood that the input layer just accepts the input. Right? Now here x1, x2, x3, xp. Now the x1 will be denoting the feature of a data point or a sample. The first feature of the sample. Second feature, and as such, I have n features here. Okay. Now what I say here is the input will be corresponding to a data point or a sample within a given data set, which are features. Now, if I have a sample which has 10 features, this will be P will be 10. So x1, x2, x3 till x10. Okay. Now, if I take a neuron of the input layer, so this will accept only one input. Right? If you see, each neuron will accept only one input. Right? No, not more than that. And it will have a weight equal to 1. That means here there will be weight, but which is equal to 1 and which is not adjustable. That is not learned, which is fixed. So I say that an neuron in the input layer will accept only one input, and the weight corresponding to that input will be 1, which is not adjustable or which is not learnable. And even the bias term will not be there. It is removed. That means the weight W0 will be 0. There will be no bias term. Okay. So in that way, we can say that if a sample, if a data set, if each sample is described by 10 features, if I want to give it as the input for a feed-forward network, the input layer should contain 10 neurons. Each neuron accepting one particular feature, and there will be no weights here. Okay. Now moving forward, this is the hidden layer, first hidden layer. Now each neuron in the input layer is connected to all the other neurons of the hidden layer, first hidden layer. Now if I take a neuron in the input layer, the output from that is connected to this neuron, second neuron, third, fourth, and this one. So it will be connected to all the other neurons. Similarly, the second neuron will be connected to all the other neurons. This will be connected. And this is what we call it as fully connected. We earlier came across a term known as fully connected. What is fully connected? If I have a layer, two layers, right? First layer and the second layer. When the neurons of the first layer, if I take a neuron, any neuron from the first layer, it will be the output of that neuron will be connected to all the other neurons of the subsequent layer. That is what we call it as fully connected. So if we take this neuron, it is connected to this neuron, all the other neurons. Again, this neuron, all the other neurons. So that is what we call it as fully connected. Again, each of this connection will be governed by a weight. Right? This connection will have a weight. This connection will have a weight. This connection will have a weight. This connection, all the connections will have a weight. Right? And those are adjustable. Those are parameters. And there is no conditions on it. It can be same, different, nothing. We don't have any restrictions on it. Right? So normally we call the weight relating to the layer 1 as W1. We address it as W1. So what is W1? The weight or the connection weights connecting the input layer neuron to the first layer neuron, first hidden layer. Okay, this is layer 1, layer 2 sort of thing. Okay. Again, so we know that the input layer numbers, neuron numbers will be dependent on the number of input features, but there is no way we can say that the hidden layer should contain this many number of neurons. It can vary, and all the hidden layers should have the same number of neurons. That also we cannot say. The only thing what we can say here is all the neurons belonging to a single layer should have the same activation function. Okay. Again, the same thing. The first hidden layer, all the neurons are connected to all the other neurons of the subsequent layer, and we call it as W2. Again, there are weights here. It can be different, same, the other thing. Okay. Similarly, so it can have n number of hidden layers. There is actually theoretically we can have any number of hidden layers, but in a practical aspect, whether it makes sense, no. Actually, for a feed-forward network, we normally restrict it to 2 to 3. Because beyond that, for a feed-forward network, for a classification and regression problem, that actually does not make sense as such. We cannot get much performance improvements by increasing the hidden layers. Moreover, it will increase the computational cost and sort of maintaining those. And now, relating to the output, now the output, the number of neurons in the output layer depends on the number of output we require. If I'm using a multi-class classification, if I have 4 classes, the number of neurons in the output layer would be 4. Right? If it is a regression, simple single value regression, it will be only 1 neuron. If it is a binary classification, 1 neuron. But if I want to require multi value regression sort of it, the number depends. So what we can say here is we can have a intuition of determining the number of neurons in the input layer and the output layer, but we cannot with certainty, or there is no theoretical background on supporting that how many number of neurons should be there in the hidden layers or the number of hidden layers as such. Okay. Now, this is what a normal architecture of a feed-forward network is. So we have a layer. It's organized into a layer-wise manner. The first layer we call it as the input layer. The last layer we call it as the output layer. And in between layers we call it as the hidden layer sort of thing. Okay. This is what the just to what we have discussed just to this. So we have an input layer. The activation function is linear. That means we don't have any activation function as such. Right? It will just take the input and just pass it on. So that's what the intention of the input layer is. Right? So it depends. The number of neurons depends on the number of features that needs to be processed. Okay. Now, hidden layer, we can have a set of activation function depending on what task we are doing. We can have ReLU, leaky ReLU, tanh, sigmoid, anything. So actually it introduces nonlinearity, or we can say that it actually performs a sort of feature transformation there. But when selecting the activation function, one thing which we need to focus here is known as the gradient behavior. It should not be, it should be efficient. The propagation should be efficient. Now, output layer, it depends on the task, the activation function, right? So if we are going for binary classification, we can have a sigmoid function, right? Binary classification, output layer will only have 1 neuron, and the activation function of that will be a sigmoid function. And if I go for a multi-class classification, it will be a softmax function. And the number of neurons in the output layer will be determined by the number of classes you are trying to estimate or you are trying to predict. Okay. And the last linear, if you are using for regression, we normally fix the output function as linear. That means whatever output we are getting, we transfer as it is. So basically, this is what the configuration of a feed-forward network would be. Right? So basically, it can be used only for 2 tasks. One is classification and the other is regression. Okay. Now let us see the mathematical sort of thing and why we call it as a universal approximator sort of thing. Okay. We have the X as the input. I think we have already seen it. So this represents the feature, right? This is one sample. So if you want to represent n number of samples, so it will be something column, first column, second column, third column sort of thing. We can represent it as a column sort of thing. So that is, so X represents the set of all inputs. So it will be having P input. S is the output, which is y0, y1, ym. Okay. Now W is a set of weights. So we have already seen that W1 is something like a set of all the weights, right? Connection. So it is from input layer to the first hidden layer. Right? So there, each neuron in the input layer will be connected to all the other neurons in the output layer. So each connection will have a weight. So all those weights we call it as W1 here. Okay. For simplicity, we call it as W1. And this is W2, wherein the first hidden layer is connected to the second hidden layer, and those connection weights we call it as. Okay. And WL means the final hidden layer connected to the output layer. Okay, those ways we call it as W. So we can say it as W. So in short, we can say that WL, that means Lth layer will have a represented as IJ. Now this nomenclature is common, where actually we can either say that I is the previous layer, right? So we can say that if I say W1, I 1, 2. So W1 denotes the weight from the input layer to the output layer. So this can be 1. I can be 1. So the 1 denotes the number of neuron in the previous layer. So for instance, if I take this connection, this is 1 and this is 1. So I can say it as W11, right? Where the first one denotes the neuron number of the previous layer, and the second number denotes the number of the neuron, which number neuron is in the second layer, or vice versa. You can, the nomenclature of IJ is just to denote the number of neurons of the layer. So you can use either way, right? You can use I to denote the second layer and J to denote the first layer, or vice versa. Okay? So that is what this IJ is denoting, and we have this. Okay. Now, for the neuron which we have seen, the output is something like this, right? The S will be something like this. Okay. So we can move into inter, right? Now this is X, which came from the input layer, because all those are linear. So what all things we give as input to the input layer, which will be coming in, right? Which will be multiplied by the W1 weight, right? W1 weight means the connection weights connecting input layer to the first hidden layer. Then we apply the activation function. This is layer 2 activation function. Layer 2 is the hidden layer, first hidden layer. So we apply it, right? Fine. So what output we get, we again multiply with W2. W2 means the weights, right? The connection weights connecting the first hidden layer to the second hidden layer. Right? So what it operates on, it transforms, it multiplies that weight to the output of the first hidden layer, right? And it goes on, right? Ultimately, what output is generated from the fourth, that means the last input layer, last hidden layer, is multiplied by the connection weight, right? Connecting the last hidden layer to the output layer, and we get this. Okay? So this is what the output. Now, if you see this, we can generalize in this manner, right? Right? If you see this, this is something like a function approximation, which we have done, right? F of G, composition, H composition, where, so this is something like a function mapping, right? It's a something like one function, which is composed by another function, which is again function composed, right? Now, actually, feed-forward network is a composition of different functions. And this is the ability which makes the feed-forward network as a universal approximator. We can learn any decision surface with this characteristic. Right? So mathematically, we call it as the function composition, and this makes it really great. And this is why the property of universal approximator or approximation comes into the feed-forward. Okay. Now again, what is our objective? We designed a feed-forward network. We have to learn all these weights, W, all these W's we have to learn. So if I have taken a single neuron, we have to learn weights only depending on the number of inputs. If there are n inputs, I have to learn only n plus 1 weights. That means one is for the bias, other for the weight. Okay. Here also, again, we bring in a loss function. Any loss function can be used. Okay. Right. And it will be a function of the B denotes the desired output, and S is the actual output, what we are receiving. Okay, so it will be a function of both, and we are trying to find out a suitable W which will minimize the loss function. Okay. Now the commonly used loss function for feed-forward network is mean squared error for regression. So if I am using for regression, I should use mean squared error as loss function. Okay, or mean absolute error. So we have two loss function, either mean squared error or mean absolute error. Commonly, we go for mean squared error because it is computationally efficient and the gradient calculation is simple, right? And for binary classification, I think you have already come across binary cross entropy, right? When you are learning logistic regression. So this is binary cross entropy. If we are going for multi-class classification, we have to use categorical cross entropy. Okay, so we have already defined what L should be. So one factor is the L should be chosen in such a manner, such that it should depend on the task which is given to you. If you are using a regression, you have to take these cost functions, and the other for binary or multiple classification, you have to. Okay. And this is exclusive for feed-forward. Right? When you go and study the other advanced models, this actually the loss function can be different. It might not be this sort of a preliminary sort of thing. There might be other, there would be coming other most, even if there might be a no desired output, B term might not be there. And for this, we restrict our, so this might be the different set of loss function that will be. Okay. Now, our task is actually we have to understand how the learning happens. Learning happens means how actually the weights get adjusted in a feed-forward network. Okay. In a single neuron, we saw that we just need to differentiate which weight we need to adjust. We differentiate it with loss function with respect to that, and we get increment parameter delta W. We just add it and just go on until we are satisfied with the what optimal value we have. Means depending on the loss value we get, if we are satisfied with the minimum loss value, we stop there, otherwise we continue. Okay. Now, feed forward in a feed forward network, neural network learning. What is the objective? We need to come up with optimal values of the weight. Okay. So what weights we do have? Here actually we have two hidden layers. So this will be the weight. This will be, so each connections will be having a weight. So all those are parameters. Here again, all these are parameters. All these are parameters. Okay. Now what is known to us? The only thing what which is known is the input. What input do we have? And actually what output is received. Okay, what output is received, and we also know what should be the output which has been generated. So for this given input, what should have been the output. Okay, but instead of that, what we received. Okay, now if we adjust this way, suppose if I consider this, I know this output, right? But I don't know what this neuron should generate, such that this neuron should generate the appropriate value. Okay? So you understand what I said? See, if I want to adjust the weight of this neuron, the last output layer neuron, I know what output it is generating. I also know what it should have generated. Right? It is something like 0.6, the actual value might be 0.8. So I know what output should be generated. Right? So I know what is the error it does. Now what about, so here it generated 0.6. Now what this neuron should generate output such that it should get 0.8. Right? I got 0.6, which is an error, right? So I know the error which this is generating, but I don't know actually what is the error this neuron is generating or inducing, such that it is resulting into a 0.6 value. The other thing is how this has to be corrected. That is what the major problem in these sort of neural networks. Okay. Now for that, we use a concept known as back propagation of error, or gradient propagation. It's simple, straightforward thing. Okay. What we do is, if you want to adjust any weight you adjust, you just do this, what we have learned in earlier thing. Okay. If you want to adjust this, you differentiate L with respect to that particular weight, you get delta W. Right. And that is what we actually need to understand how this is happening. Okay. Now this learning process has 4 steps. So we call it as the backpropagation learning rule, or the neural network learning. Okay. So it has 4 steps. One is, what we have to do is you show the input to the model. Whatever input you want to give, you give the input to the model, right? And you generate the output. Okay. So if you have 8 samples, each sample is represented by 10 features. You give one sample, 10 feature at a time. Then next, you give it, right? And you generate the output, store that output. That step we call it as the forward propagation. Okay, we call it as forward. What is forward? Simple, straightforward thing. What happens? We have the samples, we present it to the network, we generate the output. Okay. Next, loss computation. Okay. So at the output layer, we actually know what output it should be generated. Right? And using a loss function, we have the generated output as well as the output which we actually require. So we find the difference, or the loss function. Using a loss function, we find the error, how much it differs. So the second step is loss computation. So first we computed the output. Using the generated output, we computed the error, in which for which we made use of the loss function. Right? Now, I got the error of the output layer. Now in some manner, what I do is, I backpropagate the error to the interior neurons, okay, with respect to that weight. So what actually, I got this error, right? And by what amount the internal neuron weight has to be adjusted. So I pass some information then. So that is what we call it as back propagation. We call it as back propagation error. So we can see how this back propagation actually happens. Okay. Now, once this information is reached there at that particular neuron, we can update the weight. Okay. Now, this happens in a recursive manner. So each learning step, so if I say learning is happening, each learning step consists of these 4 steps. One is the forward propagation. The second is the loss computation. Third one is back propagation, weight update. Now here, back propagation is something like which we need to be focusing on. So back propagation is something wherein I know the error at the output layer. In some manner, I am propagating that information to the internal neurons so that it can identify what adjustment has to be done with respect to that weight. And now once that weight is obtained, we can do the weight. And now this is done in a recursive manner. So each step will consist of these 4 steps. It will be done simultaneously for some epochs, we call it as epochs, for 10, 100, 120,000, 20,000, it can extend. Unless we are satisfied with the performance of the network, we continue this step. Clear? Now let us understand actually what is back propagation and how this is happening. Okay, we can consider one neuron at a time, so we can just understand. So if I take a single neuron of the output layer, right? So I have a just neuron, one neuron. Okay, it has an output here. Clear? It is an output here. Clear? I have to adjust what weights this weight. This weight I have to adjust, right? This weight I have to adjust, this weight. So 3 inputs are coming to this. So I have to adjust 3 weights there. Okay, let us take one weight, this weight. Okay. Now what is said that what you do if you want to adjust this weight, you take the derivative of the loss function with respect to that weight, multiply by the learning factor. Okay. Now let us take the error or the loss function as the mean squared error. Okay. So this is the general format. What B denotes the desired output, and S is the actual output. What means actual output what I have generated. Okay. Now I have to differentiate it with this weight. Okay. For the time being, let us consider this as the x weight. Okay. I have to differentiate this function. Okay. Right. So what happens when I am differentiating? First thing happens is this is a constant, 1 by 2m is constant. M is actually the number of samples we have. That is what the average is. Okay. So this is a constant, 1 by 2m. So I take it. Now this is a function, x square. I can say that it is a x square function. So when I differentiate it, it becomes 2 into b minus s, correct? Right. So then 2 gets cancelled. So we just need to focus where we are going on. Okay. So I get a b minus s term, and again this has to be differentiated. B minus s has to be differentiated with respect to x. That means the weight. Okay. Now with respect to this weight, b will be a constant, right? So b will be a weight factor. B will be a weight factor. So it always acts as a constant. This will be moved up. So that will become 0. Now S is the output, actual output. Now what is S here? S is actually a composition of function. This something, right? Where FL is the output function of this neuron, output layer. WL is this weight, right? This collection of all these weights. FL minus 1 is the output function of this layer, and so on. Okay. Now suppose I am differentiating with weight with respect to weight L. So what I have to do, I get something like F dash L, right? Now inside that, what I get a weighted summation, right? Weighted summation means this weight. I have a weight here, first input into input of that weight, right? This weight into the input of that. So it will be a weighted summation. Out of that, only one term will be having this weight term. Okay. So I get only one term here. Okay. So in short, what I'm trying to say that when you differentiate this loss function with respect to a weight here, right? And if I want to update this weight, this particular weight, connection weight, it depends on, or it will be a product of the input, input coming here, right? So what is the input coming here? Actually is the output of this neuron. So it will depend on the output of this neuron, what value it generates, into the derivative of this particular, the activation function of this particular neuron, the derivative of the activation function of this neuron into the error term of this particular thing. Clear? So if I want to adjust this weight, it depends on the what we say, the input coming here, the gradient of the activation function here, and the error term. Similarly, if I take any other weight corresponding to this neuron, it will be the input coming there, the derivative of that plus into the error term. Okay. Now, if you take any other neuron inside, if you continue this derivation, if you write it down and continue the derivation, what you can see there is, if you want to update this weight, this particular link weight, it depends on the input coming here in this connection. What is the input connection coming here? The output of this neuron. The output of this neuron, right? Then the derivative of this neuron, activation function of this particular neuron into the weights here, because the weights will be constant there, right? The weights of this neuron, right? This connection weight, right? Then the error. Right? So in short, I can say that if I want to update the connection of any one connection, it depends on the output input coming on that connection into the derivative of the neuron to which it is acting as the input into all the connection which is affecting, or the weights or the connection weights to which the output is going. Okay, so that is what we call it as, that is what comes up. Now, back propagation means once the weight has been, the error has been calculated, for calculating this particular, I require the gradient of here. I require the gradient here. I would require the error here. So once error is generated, the error from here has to propagate till here back. So that is what we call it as back propagation. Right? So that is what is happening. As I think when we see the implementation aspect, we can have. So first step is something like we give the input, right, and generate the output. Second step is we calculate the error here. So once the error is calculated, we propagate it back. Now, what is propagating back? The error as well as the gradient of that particular neuron. How to find it? Just simple. This is the general format. You just differentiate it with respect to the weight which you need to update. Now, at that time, what you say is, if I want to update the connection weight of anything, it depends on the input coming in that connection into the gradient of the activation function of the neuron to which it is acting as an input into the output of that particular neuron to which it is acting as an input. The output might be going to different neurons. So it will depend on all that part. So I have just illustrated in this example. If I'm trying to calculate the gradient weight updation of this, it depends only on this activation function, yes, and the input here. But as you move back, it will depend on multiple. Okay. Now, once this is that, the update means, or the weight updation is, we are just trying to update the weight value. Okay. Now, this is actually how feed-forward neural network functions as such. Okay, so this is one of the important aspects here. So it comes under backpropagation learning rule. The normal, almost all the text has a clear derivation of this particular aspect. And this is one of the most important learning rule used across all the different networks. Okay, neural networks. Now, there are some issues here, right? When I am propagating, backpropagating the gradient, actually it is a numerical value which I am passing on from this particular output neuron to the inner neuron. Now that numerical value tends to vanish. Vanish means becomes smaller because we are multiplying, and sometimes it is something like a decimal value, and we multiply it becomes weaker, such that the delta W will be negligible, will be almost equal to 0. Now what happens because 0? If it is 0, there is no weight updation happening there. Right? It becomes, if it is 0 or it is something tending to 0, there will be no weight updation there. Okay, so that is what we call it as vanishing gradient problem. The other problem is exploding gradient. What is exploding gradient? Sometimes what happens, the weights here will be larger. The delta W becomes larger. Why it happens? It's because due to the initial value which we set to the weights. Okay. And at that point of time, the gradient becomes, this particular value becomes huge, right? Now, when I am back propagating and when this is updating, numerically it becomes unstable and the value increases. That is what we call it as exploding gradient. Okay. Now, these are the two issues, what we call it as vanishing grading. And so during back propagation, the loss function becomes very small. That is all. So it generally happens by if we use sigmoid and tan h, actually it is remapping to, remember, if I use sigmoid, it is remapping to 0, 1. If I'm using tan h, it is remapping to -1 to 1. If I take gradient, multiplying everything, it becomes actually nearer to 0. Okay. Now that problem, due to which the weight will not update. Even if you train it for 1,000 epochs, 2,000 epochs, the weight will remain constant, and due to which the training stagnation happens or poor convergence will be happening. Exploding gradient is just the reverse, the opposite way. The values get huge, right? So the main reason is actually it gets initialization with large values. The initial weight values will be, and repeated values, the derivative becomes more larger, and we don't normalize it. Okay. Here again, the loss function oscillates, and the training tends to fit. Okay. Now this is what the mitigation. What we can do is we can use ReLU or its variants. We can use batch normalization, which is common to both. We can use for vanishing gradient as well as we can use residual connection, which ResNet is one of the common architecture. Most common which uses residual connection. Okay, and we can initialize weight in a proper manner. Okay. Here also we can use batch normalization, or we can bring in penalty. Okay. This normally we can take care of this. So we just take what the initial values sort of things. Okay. Now we can see actually we saw the neural network. When we take a single neuron, what its interpretation is something like. Now what actually we can interpret, how we can interpret a feedback. So I've taken just a simple example to demonstrate the power of a feed-forward neural network. It's a famous problem. We call it as the XOR problem. Now, what is XOR? We have the truth table for different inputs. If I have 0, 1, it will be generating 1. For 0, 0, it will generate a value 0. Right? Again, 1, 0, it will generate a value 1. Okay. Now, what I consider is the values which is generating 1 are belonging to the same class, and the values generating 0, we are actually belonging to the another class. Now, what I'm trying to do is I want to find a partition, a decision boundary, which should separate this. What I use is I use a single neuron. So I have this is input A and input B. Since I have 0 and 1, x1, x2, and this is the bias term. So this is the bias term which we have. Okay, and what I use I use the sigmoid activation function 0. So again, sigmoid can be used for classification, for binary classification as such. Okay. Now what happens? You remember, right? Whatever we think in a single neuron, we always get a linear surface sort of thing. Right? We get a positive value and negative value. So what happens? Even if you train any number of times, I can get only to a linearly separable region space. Okay, this is the space which we get it. So it is not linearly separable. Now one problem here is if I use a single neuron, even for binary classification, if the sample space is the input space is not linearly separable, we cannot get it. Even if you use any activation function here, we cannot separate this. That is one of the major limitation of a single neuron. Okay. Now to mitigate that, what we did is we brought in feed-forward network. Okay. Now what is feed-forward? This is the input layer. So input layer just passes on, right? 2 inputs, 2 features, right? It contains only one hidden layer with 2 neurons, and the activation function is ReLU. And I have output layer only one, which is sigmoid activation function. Okay. So when I train, when we do is we can get something like this, right? Wherein the orange portion is showing one region, and the green portion is just showing another portion. Okay. Now we have to understand something like what actually is happening. Right? What happens here is this particular neuron will generate a 2 surface, 2 boundary region, right? Positive value, negative value, right? It will generate. Right? And this will again generate a positive and negative.
Sorry to interrupt you. I mean, our time is up to 9 o'clock. So is it possible to wind that?
Okay. Okay, sure, sir. I shall just come with this. Only few slides, sir.
Yeah, okay, no problem. Okay, thank you.
Okay. So this is something like which is happening here, and we get something like this surface we can get. Okay. The same as the problem with XOR problem also. This is a linear separable problem, right? And here I get a suppose something like this. Okay, so this is where we got this. So actually what is happening here is we can using this feed forward network, I can actually partition the regions into separate aspects and such. Okay. Okay. Now there are different frameworks. What we have here is we have TensorFlow, PyTorch, and Keras. I actually TensorFlow and PyTorch, actually we use them, we can get a more inbuilt or in-depth understanding of what is happening there, and we can surely use this sort of thing. I can just show for the I shall just take 5 more minutes, sir. Shall I show it, sir?
Okay, sir, please go ahead.
Yeah. Uh, okay, just a minute, sir. So this is something what the implementation look like, right? And so this is Torch, PyTorch implementation. Right? So the general class format is something like this. If you want to define a network, the class we use is this, right? And then data. Okay. So this is this function, the forward. We have to use basically we have to use only 2 function forward, which is actually for defining the forward pass, and the backward pass is something like where we are calculating the gradient as such. Okay. So we can define a simple nonlinear classification as such, where we can have hidden neural networks as such. Okay, here what I have defined is I have a single hidden layer, which is activation function ReLU sort of thing. Okay, now this is a sample data set which we have generated sort of thing. If I run this, okay, so I'm just running it. Now here I actually have defined a class here. I have taken the cross entropy loss, and this is the training loop. So this I can manually design. Okay. So this is the forward pass which I can do. Right. This is the calculation of error. The second what we are doing is, and this is something like I am passing back the gradient. So this PyTorch TensorFlow thing, even the Keras gives us inbuilt capability to do it. So you can just so this is something like we are forward, and this is what we are doing weight update using an optimizer. So I have trained it for 50 epochs. So what I do here is I'm just calculating the thing. So I get the accuracy of around 7.9. If I again train it for again 50 epochs, and if I run this, I get an accuracy of 82%. Okay, so this is what the implementation aspects are all about. Okay. And finally, what we can conclude this here is this is what we can conclude. Neural networks are general purpose learner. They assume actually it can overcome the limitations of the conventional models, but the only limitation is we require more data. We require longer training hours and less interpretability. Even we see, we try to explain only a simple feed-forward network. But if you take higher, deeper neural networks, it is very difficult to interpret. Even though if these limitations are there, it is actually revolutionizing different areas like vision, language, or sort of things. Okay. So this is actually the basics. I haven't touched on the any other advanced topics. If you have any questions, we can see. Thank you.
So once again, any questions from the side of the participant?
So can we define
Yes. Yes, sir.
Loss functions? Can we define
So it's So it's not
Those
audible, sir.
functions.
Pardon, sir. Sir, I think you are saying that whether you can, sir, can you type it on the chat box? So I think you are meant to, I just heard a partial thing. You actually, you were describing about the designing loss function. Am I correct, sir? See, design,
Yes,
yes,
yes.
it's possible, sir. The only requirement is it should be differentiable. Because we are using backpropagation, gradient propagation, it should be differentiable. And if you are designing a loss function which is not differentiable, I have shown the backward function in that PyTorch. Right? So the PyTorch framework can be used for designing loss function also. So that backward function is used to mention or describe how you should propagate the gradient of that function. So if you see the learning rule, at each level, we are using the gradient of that neural network. So if you are using an activation function, if you are defining an output function, you should also define how to find the gradient of that particular function. That's the only requirement, sir.
Oh, okay, sir.
Thank you, Pravesh, for an enriching session. Professor Praveen has started with the mathematical representation of a neuron, and then he discussed about the loss function and different activation functions. Then he gave an idea how neural networks can be used for feature extraction, and then discussed the applications of neural network. Uh, Also the famous topologies of neural networks, and explained more on feed-forward neural network. And he then proceeded to the explanation why feed-forward neural network is a universal approximator, and he then discussed about the problems with the neural network, and he concluded with a practical application of neural network to neural network for this kind of supervised learning purpose. And Praveen sir, we are proud that uh, the Department of Computer Science and Engineering, Rajiv Gandhi Institute of Technology, has a faculty member like you. And from the side of the coordinators and the ADAL FBC team, we would like to extend our sincere thanks for agreeing, for taking such a session and presenting such a nice talk on neural network, which is the fundamental pillars of modern AI. Thank you, sir.
Yeah, thank you, sir. Thank you for giving me an opportunity like this, and all the best wishes for your future sessions. Thank you, sir.
Thank you, sir. Thank you, sir.
Yes. And to participants, we are winding up today's session, and we will start our tomorrow session at 6 p.m. itself. Thank you. Have a good night.